Hello everyone. Today I would like to talk about quality control and denoising. In particular, I would like to describe a little bit the new framework that we introduced in the latest release of conn-25b. This framework brings three summary measures: data validity, data quality, and data sensitivity that jointly quantify what makes good fMRI data. To talk about this, I'm going to use an example from the 1000 functional connectomes project. Let me load. This is the NYU TRT dataset. It contains 25 subjects, 3 sessions from each subject. I'll put in the description links to how to download this data if you want to follow up this example. This data has already been pre-processed, including realignment, slice timing correction, identification, MRI normalization, and is ready for denoising, which in conn will happen here in this tab, in the denoising and quality control tab. This window is already automatically populated by conn with the default options for denoising. So in here you will see the default options that conn is suggesting for denoising. In here you can evaluate in real time, collect the different choices, how the data looks for each individual subject. And here are the 3 quality control measures, the new measures that I wanted to talk about in this video in particular. But before we talk about those measures, just to give you a little bit of context, I would like to talk very briefly about what denoising is. What is it that we are trying to do in this particular tab? The whole signal measured by functional MR imaging usually contains a mixture of effects. Some of the effects are the effects that we care about, the fluctuations in the ball signal that are related to neural activations of the areas of interest, but there are also other different fluctuations that also appear in the ball signal that we consider artifactual or of no interest. And these will be fluctuations that are related to things like residual subject motion within the scanner, but also to physiological effects such as respiratory, cardiac, or vascular effects, and also sometimes even machine effects, things that change in the scanner itself across time. And these artifactual effects can be very large, often orders of magnitude larger than the effects of interest. For example, you can see them in these carpet plots. This is the first subject in this dataset, the first session. On the x-axis, you see time, and on the y-axis, you see different voxels. The color of these images represents the magnitude of the ball signal. So this example is indicating that the ball signal was kind of like darker, lower values in this first half of the scanner across pretty much all voxels, across the whole brain, and then suddenly, after about half of the scanner time, it jumped up. The ball signal started being much higher across all voxels again in the brain. Something similar will happen here in session 2 for the same subject, but rather than an abrupt change, it was a small linear change across the scanner time. All of these are examples of scanner effects. Another example of something physiological effects, probably respiratory or cardiac effects, will be represented by something like this, where again these are very large effects that you can see in the raw signal across the whole brain. These bands or vertical bands represent changes in the ball signal that appear across many different voxels. When these effects are not controlled for, because they are very large and they also affect large swaths of the brain, perhaps even the entire brain, they tend to inflate functional connectivity measures, because the ball signal fluctuations across different voxels will all contain some portion, perhaps even a big portion of those fluctuations will be marked by these artifactual effects. The temporal correlation between those ball signals will be very high, or much higher than what it would be in the absence of these artifactual effects. And this is what we call an inflation of functional connectivity measures. They appear to be higher than what they really are without these artifactual effects. And you can see those trends even at the scale of the whole distribution. If you look at the whole distribution of functional connectivity values, this is this histogram that I'm displaying here for any sort of denoising, any changes, you will see that it's changing a lot and it's shifted towards the right compared to what you would expect. You would expect something that is relatively centered around 0. But then for every individual subject, and depending on the magnitude of those effects, you will see very extreme effects, like in this particular subject, a smaller effect, but still a very large shift towards higher values in this session. Again, you will see lack of replicability of functional connectivity caused by these large fluctuations in the whole distribution of functional connectivity values that are due to the relative different influence of these artifactual effects across sessions and across subjects. And the removal of these artifactual effects is precisely what denoising is all about. We are trying to remove these artifactual effects from the ball signal so that we can estimate as clean and replicable as possible functional connectivity measures. And one thing that we've seen time and again is that different denoising strategies or combination of strategies work best for different data sets and different scenarios. There's not one single solution that will work best for all cases. And in that context is where these measures of quality control come into play, because they provide an objective way to evaluate the goodness of your data and to base your decisions of which particular strategy and which individual parameters of that strategy you would prefer to use on your data by choosing the ones that produce the best quality of your data. So let's talk about these measures a little bit. The first measure is data validity, and it's quantified by what we call the data validity score. This is a score between 0 and 100 percentile. The higher represents better quality of the data. And what this score quantifies is the presence of biases in functional connectivity estimates. Remember the inflation of functional connectivity estimates produced by the presence of these artifactual effects. This is what this measure quantifies. In practice, what it does is measure the location of the peak in these functional connectivity distributions. If you recall, these functional connectivity distributions represent the distribution of functional connectivity values of correlations between pairs of voxels across the whole brain. So that we compute 1 million connections across the whole brain. We've plot the histogram or the distribution of those connectivity values, and this is what we represent. And we represent them before denoising here in gray, and then after denoising. And the idea is that after denoising, we hope that the data will be appropriately centered. And we quantify that level of centeredness of the data, the absence of potential biases in functional connectivity estimates, by measuring precisely the peak, the location of the peak or the mode of this distribution, and measuring its distance from zero. And then we'll compute those distances across all subjects. If you click on this button in here, the Show DB Analysis Details, that will show you the details of how this data validity score is computed. Con will show you on the top functional connectivity distributions across every individual subject in your dataset. So each one of these shapes corresponds to a different subject. It's subject 8, subject 1, subject 6. And all of these are the distributions obtained before denoising, any sort of denoising. And these are the same distributions on the same data, but after denoising for the same subjects. This is subject 15, subject 11, subject 19. And you can see for each individual subject, the distribution before and after denoising. And data validity score quantifies the level of centering of these distributions, the location of the peak of those distributions across subjects on average across all of the subjects in your data set. And that brings us to the second summary measure of quality control, the data quality score. Show that in here, this is the second measure. And in the same way that data validity score was focusing on the validity of the functional connectivity estimates resulting from your data, and the idea was that, well, in the presence of biases, the functional connectivity estimates will be inflated, and you could find potentially a significant or a statistically significant effect on average across all of your subjects, that in reality is not reflecting a true connectivity or functional connectivity between two areas, but just the shared presence of the same artifactual effects in both areas. Data quality score focuses on another complementary aspects of data validity, or the quality of your data, that focuses not what is happening on average across all subjects, but looking at the inter-subject variability, how functional connectivity changes across subjects, and whether those changes that appear across subjects in functional connectivity estimates are correlated with potentially artifactual effects also that are changing similarly across subjects. The approach used by Conn to compute data quality scores is based on a strategy first defined by Rasko-Sirik that is called QCFC, for quality control functional connectivity correlations. Sometimes it's called FD, FC for frame-wise displacement functional connectivity correlations. It goes with different names, but the basic idea is relatively simple. It tries to quantify the correlation between some quality control measure, like for example how much each subject moves within the scanner, with functional connectivity measures. You are asking the question, are there any connections where connectivity strength is related to the amount of motion in a subject, which would indicate that motion effects haven't been fully removed from the data. If you click on the button Show Data Quality Analysis Details, conn will show you the details of how this data quality score is actually computed by conn. And what conn is showing in these plots is the QC-FC correlations for 3 measures of quality control. Conn looks at the invalid scans, the number of invalid time points for each individual subject across all the functional runs that have been acquired as a measure of the quality of the data for each individual subject separately. It also looks at mean motion. This is the average of frame-wise displacement across all time points for every individual subject, measuring kind of like how much the subject moved within the scanner separately for each subject. And last, it also looks at proportion of valid scans, the proportion for every individual subject of the number of time points that have been removed or flagged as potential outlier scans from the data. For each one of these measures, let's look at invalid scans, for example. Conn will compute the correlation between the number of invalid scans across subjects and the functional connectivity strength for individual connections across subjects, and we will plot the histogram of all of those correlations across all of the 1 million connections that is testing across the whole brain. And these distributions are the ones that are shown in here. This is on the top is showing the distribution of correlations between functional connectivity and quality control measures, in this case invalid scans, number of invalid scans, across all of those million connections before denoising, and in the bottom it shows the same distribution after denoising. And for reference, it also shows this red dashed line, which represents the expected shape of those distributions under the null hypothesis. If there was truly no association between functional connectivity and quality control measures, you would expect to find no correlations, of course, but given like a small sample size, a certain amount of correlation strength, it may appear just by chance. So these red dashed lines quantify that by showing you precisely the shape of the distributions that you could expect just by chance. And from this perspective, then conn simply computes what is called the overlap coefficient, measuring the similarity between the distribution that is observed and the distribution that could be expected just by chance, and quantifies that as a percentage overlap as a measure between 0 and 100. In this case, for example, before denoising, the overlap coefficient was 39.1%, indicating that these were very different shapes, of course, and after denoising, they are very similar, and the overlap coefficient is 98.7. From here, simply data quality is computed as the minimum of the overlap coefficients across the 3 measures that have been evaluated. For invalid scans after denoising, the overlap coefficient was 98%, 98.7, mean motion 98.9, the proportion of valid scans also 98.7, so the data quality score is actually 98.7 for this particular data set. And that brings us to the third summary quality control measure, data sensitivity score. Data sensitivity score brings kind of like the other side of the coin of what constitutes having good data. Whereas data validity score and data quality score both try to minimize the presence of false positives, concluding that something is significant when it wasn't really, it was just an effect of artifactual effects. Data sensitivity focuses on false negatives, what is the ability to detect that something is significant, which depends on how much data you really have. In a way, denoising strategies tend to consume portions of your data, so to speak, either because they explicitly remove portions of the data, like in the scrubbing strategy, for example, or because they project the data into a smaller subspace, or also reducing or limiting the amount of data that you have remaining to actually later compute functional connectivity measures and estimates. Data sensitivity quantifies that aspect of having good data by how many degrees of freedom you have remaining on your data after denoising. It is really a measure of power. It uses classical statistical theory to estimate the power to detect an average effect across all of your subjects of 0.1, of a correlation of 0.1, in a fixed effect analysis at an alpha level of 0.05. This power is shown for both group level analysis and single subject analysis. The measure that is shown here is the power to detect a group effect, an average effect across all of your subjects. This is when you are interested in doing a statistical analysis that try to estimate properties of the population where the subjects are coming from, the typical random effect analysis that you would often do from your data. But it also provides here in the smaller, finer print the power for single subject sensitivity. This is the power that you have if you are trying to find significance at the level of individual subjects. Ultimately, power will depend on how much data you have for every individual subject, how long of your scanning sessions you have, and how aggressive your denoising strategy was, as well as how many subjects you have in your data set. In the process of computing power across all of your subjects in your dataset, conn also tries to help you decide about participant selection and sample size. If you click on the button Show Data Sensitivity Analysis Details, you will see the basis that conn uses to determine which subjects conn thinks that you may want to remove from your sample or not. And what it does to do so is to look at the quality control measures for every individual subject and a number of measures, and tries to identify subjects that show outlier values in any of these measures. So, for example, in this analysis, it's looking at the proportion of valid scans for every subject. Here in these plots, each individual distribution violin plot here represents a different measure, and each dot is a different subject. So this is the distribution of the proportion of valid scans for every subject. This is the distribution of mean motion, how much is subject moved across all the subjects, mean global signal change, the quality of the structural normalization, the degrees of freedom for every subject, the standard deviation of functional connectivity estimates for every subject, and the location of the peak of those distributions of functional connectivity values for every individual subject. And it tries to identify outlier subjects in these distributions. For example, it finds in this dataset that subject 24, highlighted in here, shows an extremely high peak functional connectivity value compared to the rest of the subjects. So it's looking at the interquartile range of the distribution of peak FC values across all the subjects, and is determining that this subject in particular is 3 interquartile range or above beyond the 3rd quartile of that distribution, and is how it identifies that this is potentially an outlier subject. Conn will then, by looking at these distributions, will give you a suggestion as to what subjects to keep and how many to keep and how many to remove. And this is what is displayed here in this plot, in the N24. This original dataset contained 25 subjects, and conn is suggesting to remove one individual subject with outlier score above 3, which indicates that is a potential outlier subjects from this particular dataset. Okay, so these are the 3 summary quality control measures that conn uses to quantify the quality of your data: data validity score, data quality score, and data sensitivity score. Each one of them is represented in the units of percent numbers between 0 and 100, and in general the higher values represent better quality, and we recommend researchers to try to find denoising strategies that provide at least 95% values or higher in each of these 3 measures. So let me show you these measures in action in this particular dataset. Let's start with a very simple scenario. What if we do not denoise the data at all? Let's try that. To do that, we will go here to the Denoising and Quality Control tools and select the option that says Reset All Denoising option to empty values, no denoising. And when we do that, we are basically specifying that we don't want to apply any sort of denoising. So all of the denoising options that were present before by default by conn, the suggested denoising strategy, is gone. Now we are not denoising our data. So the data before and after denoising is going to look exactly the same. How would our quality control, summary quality control measures would look like? These measures are not updated instantaneously because they take a minute to compute. So when you change anything in the denoising options and the measures that you had computed before are no longer relevant or updated, these blue buttons come up to indicate that these scores that you see here are now outdated and you need to recompute them. To recompute them, you can go here to the Denoising and Quality Control Tools menu and select the option that reads Recompute all 3 scores: data validity, quality, and sensitivity. And that will recompute all 3 scores. It starts with data sensitivity score, then it goes to data quality score, and it will finish with data validity score. Okay, this is finished now. What we see is that while data sensitivity is still very high, close to 100%, without denoising, both data validity and data quality score are very, very low. 59% for data quality and 12.8% for data validity score are well below the 95% threshold that we would like to have to indicate good quality data. Okay, so the first thing that we would do with this data is try some standard denoising strategy. We can do so in conn, selecting the option Denoising and Quality Control Tools menu, the option that reads Reset All Options to Default Initial Values. Let's click on Yes. Okay. By default, conn will provide a relatively good denoising strategy that works in many cases, and it provides a very good starting point for most datasets, or at least in my experience. These default options are specified by having anatomical core components, white matter, and CSF from 5 components from each area. We also have realignment parameters plus the first order derivatives. We have scrubbing parameters, removing outlier time points, and then we have the effect of rest, removing the potential influence of the first few scans instabilities within each individual session. So let's see how that works. If we want to see how that works in terms of our quality control measures, we can just select the denoising and QC tools, and as we did before, select the option that says recompute all 3 scores. So let's look at the results. The results are already very good. We are seeing 99%, 98% in data quality and data validity, and 100% in data sensitivity. All of the measures above 95%. So this would indicate a very reasonable place to continue with our analysis. The only caveat that we will see in here is that conn is suggesting that in order to achieve these measures, we should remove 1 subject from our dataset. Instead of having 25 subjects, we should remove 1 subject. You can look in here to see which subject conn is suggesting that we remove and why exactly does it do so. And as we saw before, this is subject number 24 in our dataset that is showing a relatively larger peak FC value, which means the center of the distribution of the subject is a little bit shifted towards the right compared to all of the other subjects in the same dataset. So in here there are 2 courses of action that we could follow. We could first follow Conn's suggestion and just remove this potential outlier subject from our analysis. If we want to do so, we don't need to do anything special. Conn is still going to continue analyzing all of the subjects. This is just a suggestion. All that we need to do if we want to remove that single subject from the final analysis is when we get to those analyses here in the results tab, for example. Let's say that we want to look at the rest condition, MPFC, and across all subjects, and that would include basically 25 subjects by default. All we do is select here the option that says add, remove, exclude outlier subjects as a control covariate, and that will enforce quality control participant selection suggestion, the removal of 1 subject. If we do so, we will see here that the number of subjects in this analysis drops to 24. This is because conn is removing that individual subject from our analysis. So that is all that we need to do if we want to follow Conn's suggestion. Second, or alternatively, let's say that we are not satisfied with having to remove 1 subject from our analysis and we want to explore if there is any possibility of keeping all 25 subjects. How would we go about exploring that possibility? We can go here to the Denoising and Quality Control tab and start by asking the question of what would the data validity score and data quality score be if we kept all 25 subjects instead of removing 1 subject from our analysis. To do that, I will click here in the data sensitivity score button to repeat those analyses. But now we would change the options to specify that we want to say exactly how many subjects we want to remove. Exactly, we want to remove 0 subjects. That is what we are saying here. So now Conn is going to recompute data sensitivity score, keeping all 25 subjects and letting us know how that changed. And of course, that didn't change much. Data sensitivity itself is still very high, close to 100%. Let's now recompute both data quality score and data validity score using these new settings. We can do that, again, clicking on the Denoising and Quality Control Tools menu and selecting recompute all 3 scores. Okay, this is done now, and what we see is that both data validity score and data quality score are still relatively high. They are all above 95%. We'll get 98.1% for data validity score and 95.8% for data quality score. So this will be a reasonable option. The data quality and data validity have dropped a little bit compared to their values when we were excluding that subject, but they have not decreased all that much. So this could also be a perfectly reasonable option that we could use as a second venue, and we could continue analysis with all 25 subjects, knowing that this still provides with the default options in conn denoising data quality, data validity, and data sensitivity scores all above 95%, indicating good quality data. Okay, and just to show you another example, let's say that we are still not satisfied. We notice that data quality score dropped from around 99% to around 96% when including this last subject. Let's try to see if we can still improve data quality score above 95.8 by changing the actual denoising options. Perhaps we can make denoising a little bit more conservative and produce better data quality after denoising without sacrificing much in terms of data sensitivity or data validity scores. Let's try that. Okay, one thing that we could try, and it will be a perfectly reasonable approach, would be to try what is called the Freestone 24 approach. Instead of using 12 parameters from realignment that include both the realignment parameters and their first order derivative, let's say that we include also a quadratic polynomial expansion to include quadratic effects. And this add up to having 24 realignment parameters instead of 12, which is going to take into account a more complex model, modeling the association between subject motion and ball signal effects. And we are thinking that perhaps this will help us improve the quality of the data. Let's see how that plays out. We can just change this option here in denoising and then go again as we did before, select the menu, the denoising and quality control tools menu, select the option that says recompute all three scores, data validity, quality, and sensitivity, and see the effect of this change, changing the denoising strategy to include a little bit more robust realignment control or control of subject motion to see whether that helps us improve the data quality and data validity score. And we see that, yeah, in fact, data quality score increased a little bit from 95.8 to 96.3, although data validity score dropped a little bit, also relatively small, from 98.2, I think it was, to 97.8% now. So this was a very small change. Got us a little better in data quality, but at the cost of a little bit of change in data validity, so it may not have played out as great as we would have hoped. Let's try something else. Another approach that we could try to make the denoising strategy a little bit more robust or aggressive will be to increase the number of anatomical core components that we include into the model. Let's try that, for example. First, I'm going to put back the realignment parameters to 6 by removing the quadratic effects. And now let's change white matter components from 5 to, let's say, 10. We double the number of white matter components. We are increasing in 5 the degrees of freedom that we are using in our data. In the previous option where we changed realignment, we increased by 12 the number of degrees of freedom that we were removing from our data. So this is a reasonable, relatively small change to try out. And again, just let's see how that works. Let's click on the denoising and quality control tools, recompute all three scores, and see how our scores change. First, data sensitivity score doesn't change, it's still 100%, perfectly fine. Then data quality score increases to 99.1%, so this is a great change. It has increased a lot with a relatively small change. And data validity score has also increased to 99.5%. So this will be a perfectly fine place to stop. We have now found a very reasonable denoising strategy just by increasing by the number of components that are estimated in anatomical core and introduced as noise modeling and removed from the data. We have managed to keep all of our 25 subjects in our data, and we have excellent both data validity scores, data quality, and data sensitivity scores. So this will be a great place to just continue doing our analysis, having very good data to work with. Once we have found a denoising strategy that we are happy with, all we have to do is click on apply and continue, this button here in the bottom right, and then click on start. Conn will apply that particular denoising strategy to all of our data. It will produce a new denoise version of our data where all of the noise has been removed, and which shows all of these very good properties in terms of the quality of this data for functional connectivity analysis. Well, that is all. I hope you found these examples useful, and I would encourage you to go and try it out. Thank you for listening, and see you around.